Oh, my computer's so slow. Applications of trigonometric functions. There are a ton because anything that follows a cycle can typically be modeled with the trigonometric function, right? So applications will be cyclical. Okay, so think weather patterns. Okay, tides go in, tides go out, tides go in, tides go out, etc. Okay, now this is a very literal translation of cyclical, but think of a bicycle or a wheel. Anything that's a wheel, if you think of a specific point on that wheel, let's say you go over a nail. Has anyone ever done that in their car? And then it's like a slow leak. And anyway, if you go over a nail, the nail goes into the bottom of your tire, and then think of the height of that nail over time. Starts at the bottom, goes to the top, goes back to the bottom, goes back to the top, right? So any sort of point on a wheel that's another really, really common application of trigonometric functions. We've already seen things like prices of particularly seasonal items, right? Or you can think, not prices, I should say demand. Demand for seasonal items. Right? So some products, just the demand stays constant, so something like milk or eggs or whatever, but something like eggnog, right? There's going to be a higher demand around the holidays, and then it goes down to basically nothing. And now you start seeing it in the grocery store earlier and earlier and earlier. So anyway, something like that. These are all, the other one that's quite common is the amount of sunlight. The hours of sunlight throughout the year, right? And of course, this depends on where you're located on the Earth. If you're on the equator, actually, this is going to remain quite constant throughout the year. But if we're relatively north, and so in the wintertime, we have less sunlight, and then slowly, we get more sunlight until summertime, we have something like, 20 hours, 19 hours of sunlight a day, and then it goes back down in the fall, right? So something like that, that's also cyclical. There are lots and lots and lots of cyclical applications. One of my favorites, actually, is the predator-prey relationship. Right? So if you think about this, think about coyotes and rabbits, right? So if there's lots of rabbits around, then let's start with lots of rabbits and not very many coyotes, right? So if there's lots of rabbits and not very many coyotes, the coyotes have lots of food, so they're going to eat lots of rabbits. Rabbit population goes down, coyote population goes up because there's so much food around. Okay, now at a certain point, there's going to be not enough rabbits for all those new coyotes because there's not enough food. There's not enough food, the predator population goes down. Now there's less coyotes, but when there's less coyotes, the rabbits start to multiply. And so it's kind of this, it's almost like you have a sine function and then a cosine function that follows. So that's a really cool one, actually. But today we're basically going to be looking at various applications and trying to connect the application to the equation, right? So how do different things that happen in this application, where does that show up in the equation? And that's sort of the goal for today. So some of this will be around, we're going to be given an equation and asked to answer questions, but the sort of more challenging piece is, let's just describe a situation. Okay, now can you come up with an equation that can model this, right? Can you build an equation based on the description of the situation, okay? All right, so let's get started. In some Caribbean countries, the current makes 50 complete cycles each second, and the voltage is modeled by V equals 170 sine 100 pi t. Okay? Graph the voltage function in your calculator and draw a sketch to include over 2 cycles. Now, before I start to graph stuff in my calculator, personally, I need to do some analysis, because one of the hardest pieces of graphing in your calculator is figuring out the window settings. Okay? So in terms of my window settings, if I want to know 2 cycles, I got to know the period of this thing, because then I want to make sure I cover 2 periods. So that's one piece of analysis that I'm going to do. And then the other piece is to get the Y window settings, I need to think about the minimum and maximum values. Okay? So first thing I see is this. 50 cycles in a second. So if you get 50 cycles in 1 second, how long is each cycle taking? Yeah, 1/50th of a second, right? So the period is 1/50th of a second. And that is confirmed based on the equation that we're given. Because in the equation, the B value is 100 pi, right? So period is also 2 pi over B, which is 100 pi, which is 1/50. Okay, so that's my period. What about my max and my min? Max is 170, yeah. And the min? Negative 170, yeah, because there's no vertical displacement here. So my midline is at the x-axis, okay? And so in fact, given this information, I don't think we need to use graphing technology here. Given that we have this grid to work with, I personally actually think it's easier to just work with the grid and the analysis around period than to graph it on our calculator. Because on the calculator, it's hard to see the scale, right? So what I would do here is say, okay, let's set my max and my min. So let's say, I don't know, this could be 170. And that's 4. So down 4 is negative 170. Okay? And then I want 2 cycles. So if 1 cycle takes 1/50th of a second, how long is 2 cycles going to take? 2/50ths of a second. Yeah. So essentially, I need my time. This is really actually voltage, and this is time in seconds. Right? So I need, for my x, min and max, I need basically for it to go from 0 to 2/50ths of a second, 0.04 seconds. Okay? All right, so what I'm going to do is, let's see, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, I like one period to be able to be divisible into fourths, because I can find those 4 key points and then just sketch the curve. So I think given I have 22 little squares to work with, I'm going to make the max at 16 squares so that I have 8 and 8. Okay, so let's see, that's 2, 4, 6, 8, 10, 12, 14, 16. Okay, so this is going to be 2/50ths of a second, which means 8 squares, 2, 4, 6, 8. This is 1/50th of a second. So what I know is that basically in this little box, I need to see 1 cycle. Okay? So this is it a sine or a cosine function? I can't remember. Sine. Okay, so sine starts in the middle on the midline, and then it goes up, 0, down, 0, up, back down to back to 0. Okay? So that's where it's helpful to divide 1 cycle into quarters. because you can go, okay, 0, max, back down to 0, down to min, back to 0. So this is one cycle. Okay, now I have to do that again because I want to see 2 cycles. So I'm going to do another sort of divvy that up into 4. So 0, 1, 0, -1, 0. And these values aren't actually 1 and -1. It's 170 and -170. But once I sort of make that max value and that min value, I can think of it in terms of graphing the base function. Okay, so here's another cycle. And there we go. Okay, so if I asked you to graph this over 2 cycles, the reason why sometimes the graphing technology can actually, I think, sort of hinder that is that I would specifically be looking for max and min. I would be looking for exactly 2 cycles. Where does that show up on the x-axis, right? How much time is 2 cycles? And then I would want there to be, I would want there to be some degree of accuracy in terms of along this cycle, where does the max happen? Where does it go back to the midline? Where does the min happen, etc.? Okay. Okay. Let's keep going. What is the period of the current in these countries? So we've talked about that already. 1/50th of a second. Okay. What do the scales and axes represent? Okay. So the axes, right? There's, in terms of the independent variable, that's time in seconds. And the dependent is voltage. Okay, now the scale, really what we did there is we set the scale to be able to see each cycle. So we've sort of talked that through already, right? What I do is I figure out my period and then I build my scale off of that. And I figure out my max and min, same sort of thing. Okay? All right, now, this is an interesting question. How many times does the voltage reach 110 in the first second? Okay. Now, what I'm going to do is I'm just going to redraw this. And this part, if you wanted to, you could do it on a graphing calculator. But if we just see the basic graph, that's 1/50th of a second, 170, -170. Okay? 110 is, I don't know, somewhere about there. So how many times does it hit 110 in one cycle? 2 times per cycle. So twice per cycle. How many cycles in 1 second? 50 cycles in 1 second. Right? So the number of times it's going to hit 110 is actually 100 in the first second. Okay? Because this period, right, this part of the graph will repeat 50 times in 1 second. Yeah?
What is going into negative voltage represent this cycle?
Okay, so did everyone hear that question? What does negative voltage mean? Okay, I need to ask Lachlan because I don't even know.
Okay, so negative voltage would actually be, because this is an alternating current, would actually be going backwards through the wire, because
Okay.
what happens is
It's like a vector.
like this, an AC/DC current.
Okay, so it's like a vector. So it indicates, the negative indicates direction?
Actually just in one direction.
Yeah. I see. Okay. There you go. I've learned something new. I feel like I knew this maybe 20 years ago, but it has slipped my memory. I think what I actually did was I purposely avoided talking about the negative part because I didn't know what that meant, but I'm glad you asked the question. I'm crowdsourcing. Okay. The wheel question. Okay. This is a very, 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 very common question. I don't think I've ever given a trig assessment that doesn't have some sort of wheel question on it. Okay? So, different ways the wheel question can be asked. It can literally be the wheel of a bicycle or the wheel of a car. Okay? It could be the pedals. Because if you think about pedals on a bike, I can't, oh my gosh, you guys, I can't draw. I'll do my best, but there's the handlebars, right? The pedals come down here and they cycle. They go in a circle. Okay, so the pedals go on a cycle. All right, here is like the famous, famous, famous trig question. It's the Ferris wheel. You get on a Ferris wheel, what is your height at any given time? You get on at the bottom, you slowly go up to the middle, then up to the top, then go back down to the middle, then go back down to the bottom. So the Ferris wheel question right, is going to look something like this. Start at the bottom. I've never seen a Ferris wheel where you get on at the top, right? Usually you have to walk up to a little platform. There's like, oh my gosh, a little ladder here or something, right? So what does this look like in terms of the Ferris wheel? Here's the wheel. Here's the little ladder to get up, right? What does the amplitude represent? Here's the middle. Top and, okay, well, we're talking about a wheel though now, which is a circle. Almost, not diameter, radius, yeah. So in any wheel question, the amplitude actually represents the radius of the wheel. Yeah. Okay? All right, so let's get going. The pedals on a bicycle have a maximum height of 30 centimeters above the ground with a minimum distance of 8 centimeters above the ground. Okay? The wheels don't go all the way down to the ground. Not the wheels, sorry. The pedals don't go all the way down to the ground. The wheel goes down to the ground, pedals don't. Okay? Assume a person starts pedaling with the pedal in the lowest position and pedals at a constant rate of 20 cycles per minute. Okay? What is the period in seconds for this periodic function? Sketch a graph of at least one cycle. And then I believe eventually we're going to get an equation. Yep. Okay. So some things that I like to do when I'm working with these types of problems is firstly, we're told about the minimum and the maximum. So let's put those in there. Okay, so I've got, let's see, 1, 2, 3, 4, 5, 6 squares to do 30 centimeters. So I'll make each square worth 5. So if this is at 30 centimeters, right, this would be at 10 centimeters. This would be at 20. Okay? So the max is at 30. The minimum is at 8. Okay, so that's one thing I want to know. Okay. What would the midline be? Think of the midline as an average. Almost. So I think some of you guys are confusing amplitude and midline. Think about these. The midline is an average of the max and the min, right? So the midline is going to be the max plus the min over 2. Because an average is when you add up the numbers, divide by the number of numbers. So that is 30 plus 8 over 2. 38 over 2 is 19. Now, where does the 11 come in? Yeah, the 11 is the amplitude. So the amplitude is half the distance from the max to the min. Okay, so if you think about distance between two heights, the distance between two heights is the difference of those heights, right? If something's at a height of 5 and the next thing's at a height of 7, the distance between those is 2. You subtract. So to get the amplitude, we have to take the max and subtract the min. Okay, so that's the distance from the max to the min, but we want to divide that by 2 because the amp is from the midline to the max or min. So that is 30, minus 8. Over 2. So that's 22 over 2 is 11. Okay. Now these are important values to know. One, to graph, but also we want to form an equation here, right? So the midline, remember, is D. The amplitude is A. Okay, let's talk about the period. What part of the description is telling us about this period? Yeah, 20 cycles per minute. Now you could make the cycle, the period 20 over 1/20th of a minute if you want, right? But what I would do personally is make the time in seconds, because then you have a whole number, right? So you can either make it 1/20th of a minute, keep it in minutes, or say, well, let's just say a minute's 60 seconds, so this is going to be 3 seconds, right? One cycle is 3 seconds, because minute is 60 seconds. Okay? Okay, now, that's the period. So I think what I'd also like to do, we know a little bit about the amplitude. We know about the midline. We know the period. Which part of the equation does the period play into? Which parameter? The b value, yeah. So the period is 2 pi over b, or the b value is 2 pi over the period, which is 2 pi over 3. Okay. Now I think before we start to look at the equation, let's actually get a look at this. So first I have, whoops. I'm just tripping over everything today. Okay. We have, let's see, 2, 4, 6, 8, 10 little squares. So I'm going to make 8 of them 3 seconds, so that I can divide those into 4, right? So there we go. Now, where does the person start pedaling? Where does the pedal start? Yeah.
When in application questions, you always want to divide the period. Like when you're about to graph the period, you always want it to be by 8, like in every case.
By 8?
Like how you did there.
Okay, so what I do is if I have 8 squares to work with, I always work with multiples of 4, right? So if I was asked here to graph 1 period, right? So if I only want to graph 1 period, I'm going to make each quarter worth 2 squares. But if I was asked to graph 2 periods, then I would make this 3 and this 6, right?
So always just multiples.
Multiple, yeah. Yeah, I find it easiest to do it that way. Okay, so where does this person start pedaling? Pedal at the lowest position. Okay, so it starts at 8. So this is where the dividing into quarters helps. 8, next quarter's middle, top, middle, back down to 8. Okay, there we go. There's 1 cycle. 1 cycle of the cycle. Okay? All right. Now here's where we get to the good part, the equation. So we have already done a lot of the legwork for the equation because we know the amplitude, we know the midline, we know the b value. The reason why I like to graph it first is because we have to make a couple of decisions here. Number one, are we going to use sine or cosine? And number two, depending on which one we use, we have to think about whether there's either a reflection or a horizontal shift, a phase shift, or perhaps both. Okay? And there are multiple ways that you could do this. So I think someone said cosine. Who said cosine? Someone said cosine. I don't know. Did you say cosine? Okay. I would probably use a cosine function as well. Because one thing to keep in mind is that sine starts in the middle. Cosine starts at the top. Okay? So if I chose to use cosine, I don't have to have a phase shift if I include a reflection. Right? So what I tend to do is if my starting point is either the top or the bottom, I use cosine. If it's in the middle, I use sine. Yes?
Is that kind of a common thing, like a question like this on a test, to ask specifically for you to make like a sine or cosine graph?
It could be, yes. So that was a good question. The question was, could I ask you to write this as a sine function? And the answer is yes. So I think what I want to do actually is let's do this a couple of different ways. Okay? My personal instinct, when I can, and maybe I'm just a creature of habit, but I tend to avoid the phase shifts if I can. So what I would do is say, I'm going to use cosine, but then include a reflection, which means the amplitude's going to be negative, or the a value, rather, would be negative. Okay? So what I would do is y equals a cosine bx. Well, actually, I should really go like this. B times x minus c plus d. Now, if I choose to use cosine, then as long as I make the a value negative, instead of it starting at the top, it's going to start at the bottom. So that's how I would probably do this, is say, okay, I'm going to make this negative 11 cosine 2 pi over 3x. Now, because I made it negative 11, there's no phase shift. Because when you start with y equals negative cosine x, this whole thing's going to reflect, flip over the x-axis, it'll start at the bottom. Okay? And then plus 19. So that's one option. Now, if you want to make cosine positive, you could do that. But now we have to include a phase shift because if the amplitude is positive, the starting point is over here. This is at 1.5, right? So you could also do y equals 11 cosine b times x minus c. So 2 pi over 3 times x minus 1.5 plus 19. These are the exact same function. Yes?
For this one, is the b value 2 pi over 3, or is it just 3?
The period is 3.
Yes. Okay.
The b value is 2 pi over 3. Yeah. Okay? You could do that. Now, because I'm making amplitude positive, if amplitude is positive, cosine starts at the top. So if I choose to do it that way, I have to include a phase shift as well, because the top has been translated 1.5 seconds to the right. Okay? There's another option. The other thing you could do is you could do this as a sine function. Now, if it's a sine function, the starting place would be right here in the middle on the upswing. That's 0.75 seconds between 0 and 1.5. Okay, so here's another option. Okay, now if I chose to do a sine function with this specific phase shift, sine starts on the upswing. So the a value will be positive. Okay. So I could make this y equals 11 sine bx 2 pi over 3 x minus c. So now I'm moving 0.75 seconds to the right to get to the start of the sine function. And then plus 19. Okay. Any of these would be fine. The nice thing is that because of the fact that cosine is simply a horizontal translation of sine, and there's symmetry to the sine and the cosine function as well, is that a lot of things don't change, right? The amplitude doesn't change. The midline doesn't change. The period and the b value don't change. What could change is the phase shift. And also, you may or may not incorporate a reflection, right? So the only time I really make the amplitude negative is when, and I tend to do that because I don't like to use phase shifts if I don't have to, but when I would use a negative amplitude is when I have a function that looks like this. Starts in the middle but on the downswing. So I would make this a sine function, because sine starts in the middle but on the upswing, and have a negative amplitude. Or for a cosine function, just like we saw, instead of starting at the top, it starts at the bottom. Okay, so here I would use negative sine, negative cosine. Make the a value negative. So that instead of having to deal with the phase shift, I'm dealing with a reflection. Okay? Now, you may find it easier to deal with the phase shift and always keep the amplitude positive. That's totally fine. But there are infinitely many ways that we can write the equation for any given sinusoidal curve. And a sinusoidal curve in general incorporates both sine and cosine. And in fact, in, for example, Math 30-2, we do something called regression, which involves, it's kind of like drawing a line of best fit. You get a bunch of points, and in science class, you draw a line. That's a linear regression. But we can do this using technology for curves as well. So if you get a bunch of data points that kind of go like this, you would do a sinusoidal regression. Now, the only sinusoidal regression that actually exists is using the sine function, because we don't need one for sine and one for cosine. We can write all functions in terms of either or. Okay? All right, so use your equation to determine the height of the pedal after 4 seconds. Well, if you plugged in x equals 4 to any of these, you should get the same answer. Okay, so let's just pick one of them. We'll just use this one. Okay, so y equals negative 11 cosine 2 pi over 3 times 4 plus 19. I don't know what that is. Negative 11 cosine 2 pi over 3 times 4 plus 19. 24.5 centimeters. Okay, now here we do need to graph this. Use your graphing calculator to determine the length of time to the nearest 100. That's pretty precise. In seconds, that the pedal is above a height of 25 centimeters for each cycle. So here we do want to graph y1 equals negative 11 cosine 2 pi over 3x plus 19, and then y2 would be the 25. Okay, so let's do that quickly. clear this stuff out. Okay, so negative 11 cosine 2 pi over 3 x plus 19. And then my second function is just going to be the horizontal line at y equals 25. All right, now I'm not going to hit graph yet. Yeah, I did all that work to figure out what my max is and my min is and my period, so I'm going to go put that all in here. I basically want to see one period, right? So I'm going to make my x go from 0 to 3, because one period is 3 seconds. And my minimum height is 8. I think I will actually keep that at 0 because I kind of like to see the ground in these types of questions. My max is at 30. So maybe I'll make this, I don't know, 35. And then I'll make the y scale 1. There we go. And there's the other one. Okay, so now I have to go ahead and find the intersection points. Okay, so that's 1.025. Okay. So here's my little picture. How many people know what this one's going to be? Look, we can just plug it in, but there's symmetry here. So it's going to be 1.025 away from 3. Yeah, 1.975. I should say the y coordinate, 25. Right? So the total time that it's going to be above 25 centimeters would be 1.975 minus 1.025, which is 0. 0 point what?
0.949. So I said, although
I think there's rounding, yeah. Why can't I do this today? Hold on, 1.025. 0, 5, 9, 0, there. 0.95 seconds. Okay. Yes, the wheel question, any sort of wheel, is a classic trig application question. Okay, last question. This is about the tide. Also a very common trig application question. On a particular afternoon, the tide in Victoria, BC reached a maximum height of 3.0 meters at 2 p.m. and a minimum height of 0.2 meters at 8 p.m. Sketch a sinusoidal curve based on these data points. Okay, so just so you know, a sinusoidal curve could be sine or cosine. Okay, they're both called sinusoidal. Okay, so I think we've already got a scale for us here. That's kind of nice. So this is time in hours. Looks like we're in 24-hour time. The maximum height occurs 3 meters at 2 p.m. So 2 p.m. would be here, 1400 hours. That's 2 p.m., right? And at that point, we are at a maximum height of 3.0 meters. So that's right here. Okay. A minimum height of 0.2 meters at 8 p.m. Okay, so 8 p.m. is what? 20 hours, yeah, and we're at a minimum at 20. Okay, we're at a max at 14 and a min at 20. Okay, so at what time would we reach the middle?
10 or
This is 2 p.m. This is 8 p.m. So what would the time be when you're right in the middle? 5 p.m. Yeah, right in the middle. There's 6 hours difference between those two times. So it's going to be right in the middle at 5 p.m. So that's at 17. Now what is right in the middle of the max and the min? The midline, yes, right? So I've got my max. This is where I actually might even start adding some more stuff in here. There's my max, there's my min. Okay, my midline is an average. So it's 3.0 plus 0.2 over 2, which is 1.6. So here at 5 p.m. or 1700 hours, I'm at 1.6. Okay, so if I even just sketch what's happening here, oh man, that's bad. Hold on, I gotta do a better job of that. Okay, that's better. Okay, how much of a cycle is that? Half, yeah. Going from the max to the min, the full cycle will be going all the way back up to the max. So at this point, I can see, okay, half a cycle is 6 hours. So one cycle, or one, I should really use the word period here. You can interchange them, but I'm going to use the word period. Half a period is 6 hours. So one period is 12 hours. And this is true. The tide goes in and out twice per day. Okay? So now what I'm going to do is I'm going to start to fill in some other points. Okay, so this was 3 hours after. So 3 hours before, it's going to be in the middle. Okay, 3 hours before that, it would be at the min. So 1, 2, 3, it's down at the min. Okay, another 3 hours, it's going to be in the middle. 1, 2, 3, middle. 1, 2, 3, max. 1, 2, 3. Now this would be at the middle, but that point is not going to be in the domain of the function because time will start at 0. I suppose you could think about it as the previous day, but we would probably just stop there. Okay, and then I could keep going. 1, 2, 3, back in the middle. 1, 2, 3, back at the top. 1, 2, 3, in the middle. Okay. There we go. Okay, so we've got the midline. We're going to come up with an equation. We've got the period, so we can figure out the b value. The period is 12 hours. B is 2 pi over 12, which is pi over 6. Okay, what would another important piece be to be able to come up with an equation? And sometimes it's helpful actually to just do this. I'm going to use h of t equals a sine b t minus c plus d. Okay? All right, so we've talked about b. We've talked about d. What else do we need to cover? Yeah, amp, right? So the amplitude is half the distance from the max to the min. So distance is a difference of two heights. Okay, so the amplitude is max minus min, 3.0 minus 0.2 over 2. So that's what? 2.8 over 2 is 1.4. Okay, so there we've got the amplitude. Okay, now in this situation, we have to include a phase shift because whether we decide to make this sine or cosine, when time is 0, it's not either in the middle or the top or the bottom. So we can't get away with just using a reflection here. We have to use a phase shift. So you could either use this point. When you're at a max, what are you at the top? What's the start when you start at a max? What type of function is that? Cosine. Or you'd have to look at where are you in the middle on the upswing, right here. Then you could use sine. So that's at, I don't know, 11 a.m. Okay, so this is at 2 a.m. And either of those would be just fine. Okay, so I wrote out sine here, but let's do it both ways. If we start where they usually start without a reflection, then a would be positive. So if we write it as a sine function, the start of the sine function, when it's in the middle on the upswing, is at 11 o'clock in the morning, 11 a.m. So we would have to make the c value minus 11. A is 1.4, sine b is pi over 6, times t minus 11 plus 1.6. That's one option. Now, if you decide to make it cosine, and I decide to start at the top, which is what I would probably do, because, you know, you could, but I wouldn't include both a phase shift and a reflection all at the same time. But it has been done before. If you decided to make it cosine, that would be a cosine b times t minus c plus d. Okay, the amplitude is the same. The period is the same, so b is still pi over 6. The phase shift now is 2 units to the right because the top is at 2 a.m. So this is going to be t minus 2 and then plus 1.6. Okay. All right. What about the domain? Yep. Yes. Time is greater than or equal to 0. Now, if you were asked, if you were talked, I mean, sometimes, depending on the wording, the time might be a day, 24 hours, but we're not really given any indication here that this is stopping at the 24-hour mark. And in fact, if you think about a tide, it just keeps going and going and going and going, right? So yes, I would argue that this is time is greater than or equal to 0. Okay? It can get a little bit gray. One example that I'm thinking of is sometimes you'll get a sine or cosine function that talks about, let's say, the average daily temperature in Calgary over the course of 50 years. Well, if you're thinking about the average daily temperature, then your domain is just going to be 1 year, 365 days, because there's only one average for day 1, one average for day 2, etc. Right? So that's sometimes where it's just one period, but in this case, we're not given any indication of that. So yeah, I would say that the domain is time is greater than or equal to 0. Okay. Any questions? We are done.